Okay, welcome to video 1.6. Okay, now, so what I'm going to do here is just show some terminology that's in green. So I want you to read the green pages 133 to 136. Now, if you read that, I think at first it looks very daunting. There's a bunch of Greek letters and a bunch of terminology, and just let me explain some things that I think will make it not be so daunting. Okay, first, okay, here's what Green writes. So I think this is on page 133. Um, First, as I did in I think the last two segments, um, define um, L of theta just equal to um, f of x1 theta. I think he uses semicolon. Green, I can't remember if Green uses a comma. It doesn't matter. Usually we think of semicolon, we say f of x1 given theta, although what we're going to do is L as a function of theta, so we're going to treat the opposite. X1 is given and theta is not. But this is times f of x2 of theta times so on times f of x in of theta. Okay, so we're assuming n total observations, and what we've done, we've said this is the probability of observing all the data that we observe, where the xt's are the realized values of our data, our independent and dependent variables, given um, given theta. Okay. Now, let me give you a hint on how to do this. So, Green talks about theta being a vector. So, it's a vector of k parameters. Just think of it as being a scalar. Okay. When you read through it first, just think there's one parameter. Like the Diermeier-Merlo problem, theta is just one parameter to estimate. Okay, it's easier when you do that. And I'd also think of the x's, so that each x1, so on, xn, that's a vector. I think that's a k plus one elements, whatever. Just assume it's just one. It's just one dependent variable. When you first read through it, think of that as the case. Okay, it's simpler and it's not as daunting as it looks at first. And once you do that, read it again, where you think, okay, now let's assume theta is a vector and x is also a vector. Okay, now next, we define log of theta as this. Then this implies that the natural log of L of theta. Okay, so the what is it? The log of the product just equals the sum of the logs. Okay, if you remember this, just the rule of natural logarithms means that log of L theta just equals log of f x1 theta plus dot 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 plus log of f of x in theta. In other words, that equals what does he use? He uses I. So I think I called it observation T. Okay, Green. I'm going to switch now. Sorry, I'm going to switch to now instead of calling it observation T and calling it I. So um, I equals 1 to n, just log of f of xi theta. Okay. Okay, so we have that. Log of L of theta equals that. Okay, now, um, and by the way, when you're going through Green, a lot of these things, where does that come from? A lot of those pages, 133 to 136, It's just definitions, okay? So you just think, well, wait, why is that true? Well, it's just because Green decided we're going to define this to be true, okay? And you say, why is that true? It's because it's true because I say it's true. That's always the case when you have a definition, okay? So next, we're going to define um, g of I. G sub I equals um, d theta, just the partial derivative of log f of xi theta. And this is page 134, equation D1. Okay, so um, when you're going through, just memorize this. GI equals this. Okay, next. And by the way, the first time, think of this theta as a scalar. So that means this GI is a scalar. Now, hopefully, you know something about um, taking the derivative with respect to a vector. If not, read one of those mathematics for economists books. There must be 3 or 4 dozen of them you can get on Amazon. But and hopefully all of you took the math refresher course, and it should be in that textbook. But if theta is a vector, so it's a k-length vector, so and then this log of f of x, that's a scalar, but the derivative with respect to a k-length vector of a scalar is just going to be a k-length vector. So if theta, if you go back to being a vector, this gi is going to be a k/1 vector. Okay, but first time reading it, don't think of theta as a vector. Think of theta as just a scalar. Okay, next, define big H of I just equals the second derivative of that same thing, log f of xi theta. And okay, this is also page 134, D1. Okay, so again, if theta is a scalar, that means gi is going to be a scalar. It also means capital HI is a scalar. Okay, now if theta is a vector, if it's a k-length vector, gi is going to be k/1, and hi is going to be k/k. Okay, it's not that critical to know, but when you read it the second time, you should be aware of that. Okay, usually in this course, we use capital letters to denote a matrix. This HI is going to be a k/k matrix. Okay, but for now, everything's a scalar, so it's 1/1. Okay, now define G just equals the sum, I equals 1 to n of all the little gi's. Okay, so again, if you're reading that and it says, where is he getting that? Just remember, it's a definition. Okay, Green just says, I'm defining this to be true. Okay, so I'd memorize some of these, that definition, that definition, that definition, that definition. Memorize it before you start reading Green. Okay, so define that as true. Define H equals just the sum, I equals 1 to n of the HIs. Okay. So, okay. Therefore, okay, HI is the second derivative of that log, okay? Big H, just H without a subscript, just equals the sum of these terms, okay? Now, hopefully you remember from freshman calculus, the Sum of the derivatives is the derivative of the sum. Okay, hopefully you remember that. So if you remember that, okay, so if we had um, h is just, we put a sum right there. Okay, so h equals the sum of the derivatives. It also equals the derivative of the sum. So it's got to equal d squared d theta squared sum I equals 1 to n log f of xi theta. Okay. Equals derivative of the sum. Okay. And then the same is going to be true. G is going, big G without a subscript just equals the sum of the GI's. Okay. It's the same thing. Equals, just put a sum there, but it's also got to equal the derivative d theta of the sum. And that's just from that rule from freshman calculus. Okay. So we define it, G, to be that, but because of our rule in freshman calculus, we know that G has also got to equal that. Okay. We define H to be this, and because of our rule from freshman calculus, H has also got to equal that. Okay. All right. Now, okay, I think I'm going to come back to this. So you got to memorize some of those definitions before you start reading Green. That's what I recommend. Okay, next, okay, Green writes, define well, let's call it definition. Wait, excuse me. Green writes, theta hat is defined to be okay, he writes the, okay, and I'm going to put parentheses, maybe he should have written A, is defined to be the theta that maximizes L of theta, where L of theta is the likelihood function that we just defined on that earlier board. The reason I put A, you never know if it's a unique maximum. So we have L of theta and theta. You never know if theta could look like this, where, you know, there's 2 points that it's maximized. Or maybe it looks something like this. Maybe it looks like a hill with a plateau on it. Looks like this plateau, like that. So there could be a, you know, continuum of points that maximize it. Now, usually any homework problem you have, usually in practice, L is going to be well defined. There's going to be one unique maximum. Okay, if that's true, if there's a unique maximum, then it's fine to say the. But otherwise, you never know if that's true, that L has a unique maximum. So maybe Green should have said is A. Regardless, Green assumed that that it's maximized at a unique value. There's a unique maximum, so theta is, we'll define it to be that value that maximizes L. That means theta hat maximizes L of theta, which equals big pi, that's the product, I equals 1 to n of f of xi of theta. So that was just f of x1 theta times f of x2 theta, f of x3, and so on, okay? Theta maximizes L, okay? L is defined to be that function, okay? Okay, before we just wrote that out, f of x1 theta times f of x2 theta times x and so on. But another way of writing it just with the big pi, okay? Theta maximizes L theta, okay? Therefore, theta also maximizes log of L of theta, okay? And the reason is just that former board, this one, that I did from lecture 1.5. If log is a strictly increasing function, okay, theta maximizes L of theta, then theta hat's also got to maximize log of L of theta, okay? Okay, given that, okay, theta hat maximizes that, so that means the derivative of log of L of theta with respect to theta has got to equal 0 when theta equals theta hat, okay? Therefore, d theta log L theta, sorry, my handwriting's bad, log of L of theta equals 0, okay? Equals 0 when, when theta equals theta hat, okay? All right, okay. Okay, now, log L of theta equals summation I equals 1 to n log of L. Wait. No, sorry. Log of f of xi theta equals that, okay? Therefore, okay, this implies that the derivative, if we take the derivative on both sides, the derivative d theta of log L of theta has got to equal the derivative of this term, the derivative of the term on the right. Okay, now, the derivative of this term on the right, so it's the derivative of the sum. We know from our rules in freshman calculus that the derivative of the sum is the sum of the derivatives. So I'm going to skip a step. I'm going to say that's just got to equal I equals 1 to n, the derivative of the equals the sum of the derivatives, log f xi theta. That's what I wanted. Okay. Now, let's go back to the former board. G of I, we just defined it to equal the derivative of the log of f of xi, okay? So in that former board, we defined this to be g sub I, okay? So that just equals I equals 1 to n g of I, okay? And how do we do it? So and then, and by the way, we can write g of I. Turns out it's a function of theta. Okay, so I'm going to write that explicitly now. So this term is g of I, but now it's called g of I as a function of theta. But now we defined g as just the sum of all the gi's. So what we have here, same thing, the sum of all the gi's, that just has to equal g, and I'm going to call it g of theta now. Okay, so therefore, we have the derivative, wait, so we have the derivative, so this here, the derivative with respect to theta, that's just this term here. Okay, the derivative of the log of the likelihood with respect to theta has just got to equal g of theta. And now we've shown already that when we take the derivative of the log of L of theta, set theta equal to theta hat, it's got to equal to 0. So all that means is this and this, put them together, it means that g, when theta equals theta hat, g of theta hat just equals 0. Okay, and that's page 136 of Green. Okay, so Green goes through from page 133 to 136 just to show this. Okay, hopefully if you've followed this, it may look daunting when you first read Green, but if you've seen this, once you see it's not as daunting as it looks. Okay, so that's the final part that Green shows, and that's the last of that section, those 4 pages that I want you to read. Okay, I think that is all. Okay, so that what I'm going to do. So that was. So by the way, this is the first lecture. You are not required to read anything for this lecture, and this is what I'll typically do in lectures. So I'll go through in my lecture, I'll go through what you were supposed to read, and then at the very last, take something like 20 minutes, something like maybe 30, I'll pick a little bit of the hardest part of next week's reading and just show you, here's some of the hard parts, here's what I want you get a taste of what you're about to read, and that's what I've just done. So in this, which is lecture 1.6. This is just part of the reading that you're supposed to do for next week. Once you get a little taste of it, we'll talk a little bit more about it in next week in lecture 2. Okay, so that was 1.6, and that finishes lecture 1. Okay, see you next week in lecture 2.